This presentation details a series of observations and experiments that challenge accepted scientific beliefs about light. Anyone who wishes to replicate the experimental observations can use an inexpensive acrylic prism. Hold the prism with the apex up above your eyes and view a well-lit window surrounded by a dark or dimly lit wall or door. You can adjust your viewing angle until you observe a blue fringe just above the top of the window, a cyan fringe at the top of the window, a yellow fringe at the bottom of the window, and a red fringe just below the bottom of the window. Notice that the blue and yellow fringes are wider than the cyan and red fringes. Contrary to what modern physics courses teach, prisms do not refract different colors of light at various angles. Instead, prisms separate light into red, green, and blue panes. Later experiments will demonstrate that all colors refract at the same angle. In contrast, the separation of colors is not refraction but deflection of the blue pane toward the apex, the red pane toward the base, and no deflection of the green pane. For viewers who are artists, please note that the colors of light don't mix like colors of pigments. For example, yellow and blue pigments make green, while yellow and blue light make white. The white and yellow layers of this slide demonstrate that mixing. Next, place a pencil horizontally between the prism and the window. Notice the yellow fringe above the pencil, red fringe along the top, blue fringe along the bottom, and cyan fringe beneath. The pencil's presence blocks all light and emphasizes the deflected color panes. Notice that red and blue are in the dark areas, while the green component of yellow and cyan remains in the bright areas. That is your subtle clue that the green pane is not deflected. Further experiments will demonstrate that more clearly. In a more typical rainbow scenario, a much narrower band of light permits red, green, and blue to completely separate from each other to produce red, yellow, green, cyan, and blue. If you have a very steady hand, you can simulate the necessary narrow slit by moving your pencil toward the top of the prism. A raindrop or other imperfect prism often mixes the colors to also produce orange, indigo, and violet. This slide demonstrates that the transition from lighter to darker or darker to lighter produces the colors, as Johann Wolfgang von Goethe observed over 3 centuries ago. Please pay particular attention to the top of the gray circle. Notice that the blue and cyan fringes at the upper left align with the yellow and red fringes at the upper right. Similarly, the yellow and red fringes at the lower left align with the blue and cyan fringes at the lower right. Those fringes demonstrate that different colors do not refract at different angles. Please refer back to the prior slide if you need help understanding how deflecting red and blue color panes produce the effect you observe on this slide. Since you now understand how prisms work, this slide demonstrates that white light consists of only red, green, and blue. Look at the white and black lines through your prism with its apex pointing left or right. Pull the prism back far enough from the page to see the white line completely separates into only red, green, and blue. Similarly, the black line separates into only cyan, magenta, and yellow. Notice that blue is slightly wider and deflects slightly farther from the green line than red. Chapter 7 of my book, the Luminiferous Aether, explains this in great detail. Now, observe directly under the green line on the black background is a magenta line on the white background. Magenta is blue plus red. Green is still absent from exactly where the black line was, whereas red and blue deflected in opposite directions to fill the place that was a black line. Green is only absent from the black line, where it never was. Directly above the black line, only an undeflected green line remains where the white line once was. That is how you know green doesn't deflect at all. Pause the video and think about that if necessary. Next, observe that directly under the red line on the black background is a cyan line on the white background. Cyan is green plus blue. Red is still absent from where the black line was, but the entire red color pane is now shifted toward the base of the prism. Finally, observe that directly under the blue line on the black background is a yellow line on the white background. Yellow is green plus red. Blue is still absent from where the black line was, but the entire blue color pane is now shifted toward the apex of the prism. Note that the behavior of white and black lines from the prior slide is critically important for understanding absorption and emission spectra. This slide depicts the visible light portion of the Balmer M equals 2 series of the emission spectrum for hydrogen. Due to spectroscopy's importance to astronomy, many prominent scientists theorized about the meaning of those spectral lines in the late 1800s. From that work, the theory of quantum mechanics was born. Viewers should suspect that something may be amiss with spectroscopy, since many of those spectral colors result from overlapping red, green, and blue. For example, notice how the 486 nanometer cyan line is nestled between the 434 nanometer blue line and the 656 nanometer red line, yet there is no 509 nanometer green line. Since cyan is a mixture of blue and green, how can blue be present but green be missing? Chapter 8 of my book explains the spectral lines of quantum mechanics in much greater detail. This slide is Table 8-1 from my book, The Luminiferous Aether. It depicts a portion of the Balmer M equals 8 series spectrum of the hydrogen atom. My prior presentation, How the Ether Produces the Fundamental Constants of Physics, explains why all color mixing occurs at the Bohr radius within the hydrogen atom. This table shows how red, green, and blue mix at the Bohr radius to produce the illusion of other colors and the associated illusion of quantum levels. Please note that the blue band is at least twice as wide as red and deflected slightly farther than green. That should seem familiar from the behavior of the white line 2 slides ago. Since there are only 3 colors of visible light, all other colors are figments of our imagination. Consequently, the theoretical quantum levels corresponding to imaginary colors can only result from mixing red, green, and blue. For the current and future scientists among my viewers, I hope my presentations have given you many ideas for future research. Thank you for viewing.